All right, section 3.2. So here we're going to start graphing the functions that we're working with in 3.1. Now it's not as bad as it sounds, and mainly because kind of like in 3.1, we're going to ignore some of the details. We're going to focus on some of the important parts, like the x-intercepts, the y-intercepts, and we're also going to use the end behavior we learned about in section 1. Okay. So if we have a function like this, which is in factored form, which is nice, you'll see why in a minute. How do we find the x and y intercepts of the following function? That's something that's going to help us graph these things. Okay, well, first of all, if we have just a regular old function, let's say we have an x-axis and a y-axis here, and then I want to find the x and y intercepts of, let's say we got a line here, just making it simple. Okay, well, how do I find the x-intercepts? Let's find this point first. Well, what do we know about that point? Well, it has an x and a y value, and then, well, what do we know about the x and the y values? Well, I'm not sure what the x value is. I'm not sure how far over I am, but how far up am I from the x-axis? In other words, my y value is 0. So if I want to find my x intercepts, I just want to plug in y as 0 to my equation because I know that that's true at that point. I know my y value is 0. What's true about my y-intercept? Okay, well, that's going to be some point as well. And what do I know about that point? Well, to get to that point from the origin, I go over 0 and then up. That's what I'm trying to figure out, how far up. Well, we know the x value is 0. So to find the x-intercepts, I plug in y as 0. To find the y-intercepts, I plug in x as 0. And we can plug those into our function. Okay, and that works for a line, a parabola, an absolute value function, anything. Okay, including a big polynomial expression like this. Okay, so again, to find our x-intercepts, then we want to set y equal to 0. And for our y-intercepts, we want to set x equal to 0. Okay, so let's do that. If we set y equal to 0, so we have 0 equals this stuff. Well, when is that going to come out true? When x is what? Well, if I'm multiplying these three things and my answer comes out 0, then I know at least one of these three things has to be 0. And that's going to happen when x is -2. So we get -2 comma 0 is one of our x-intercepts. -4 comma 0 is another x-intercept. And then +1 comma 0 is our last x-intercept for this function. Okay. Next, what is our y-intercept going to be? Well, if I plug in x is 0, I get 0 plus 2 is 2, 0 plus 4 is 4, and 0 minus 1 is -1. So multiply these numbers. 2 times 4 is 8, times -1 is -8. So then we get the point 0 comma -8. Okay, and then that would be our y-intercept for that function. Okay. We're going to use this stuff to graph in just a little bit. Next, a little definition here. The multiplicity of a 0, and again, a 0 is just one of our answers, is the number of times that its associated factor appears in the polynomial. Okay, so we're not always just going to have x plus 2 one time. We might have x plus 2 twice, which would give it a multiplicity of 2. Okay, so for example, down here, read along with me, the 11th degree polynomial, and they give us the polynomial here because I have this thing 4 times, this thing 7 times. If I multiplied it all out, we'd have x to the 11th somewhere in our polynomial. So this is an 11th degree polynomial, which should have 11 answers. Okay, so this has the zeros, x equals -3 and x equals 2. Like it says here, the solution of x equals 3 has a multiplicity of 4 because this factor occurs 4 times. In other words, instead of using exponents, I could write x plus 3 times x plus 3 times x plus 3 times x plus 3. And then here I could write x minus 2 7 times. Okay, and then to solve, if we set it equal to 0, to get my answers, well, I'd get an answer of -3 4 times, which is why this has a multiplicity of 4. And I would get an answer of 2 7 times. So we say that has a multiplicity of 7. Okay, so again, just a little definition there. Now, how are we going to use that when we're graphing? Well, if something has an even multiplicity, it's going to just touch the x-axis. In other words, it's going to look like it kind of bounces off the x-axis. An example of that would be right here. Okay, and then if it's an odd multiplicity, it's going to cross or go through our x-axis. Okay, so let's look at these two graphs. My answers here are my factors, I should say, are x plus 6 and x minus 7. So I'm going to have intercepts at -6 and +7, which are here and here. And then since this is x plus 6 to the first power and x minus 7 to the first power, in other words, there's only one of them, then it's going to go through or across the x-axis. In our second function, our factors are x plus 6, and I get x minus 7 twice because that has an exponent of 2, and that's a little hard to see on this page. But x plus 6 has a multiplicity of 1, so then at x equals negative 6, we're going to pass through our x-axis. X minus 7 has a multiplicity of 2, so at that x-intercept, we're going to bounce off. Okay? All right, so we're going to be using that multiplicity to help us graph these functions. All right, before we start graphing though, let's just identify a few things about a couple different functions. So we got examples 1 and 2 right here. So let's do example 1 first. Example 1, what degree is this polynomial? In other words, if I multiplied this thing out, what would my highest power of x be? Now I don't actually have to multiply out the entire thing. I would get x times x would give me x squared here, and then when we multiply that polynomial with the x minus 1, we get x to the third. So again, just multiply basically the first term in each of these binomials, and this would be a third degree polynomial. Okay, what would the end behavior be? Well, again, what would this thing be if I multiplied it out? What would my first term be? Well, it's just x times x times x, so it would be 1x to the third. Okay, well, that is odd and positive, and from section 1, if it's an odd exponent and a positive coefficient, then what type of end behavior is that going to be? Well, that's going to be low to high. Okay, what are our x-intercepts with multiplicity? So let's see, we're going to have 3 x-intercepts. Probably could have written that smaller, but that's okay. I know the x-intercepts all have y values of 0. Okay, and then where are my x-intercepts going to be? At 3, 0, negative 4, 0, and 1, 0. The order does not matter. Okay, so I'm going to have those 3 x-intercepts. And then what's their multiplicity? Well, they each have a multiplicity of 1 because none of my factors are raised to a higher power. So the little 1 underneath is for the multiplicity. Okay, where's my y-intercept? Let's see, if I stick an x is 0 here and here and here, I get negative 3. I'm going to get rid of the negatives first. Negative 3 times negative 1 is positive 3 times 4 is 12. So then we get 0, 12 for our y-intercept. Next, how many distinct x-intercepts? So distinct means different x-intercepts. In other words, nothing with the multiplicity. So here, in this example up here, we have 3 answers, negative 6, positive 7, and positive 7 again, but we only have 2 distinct x-intercepts. Okay, so how many distinct x-intercepts do we have here? Well, we have 3 different x-intercepts, so there'd be 3 of them. Okay, and then lastly, how many roots are there? So how many answers are there? Well, 3, because I get 1 answer from this, 1 answer from this, and 1 answer from this. So there are 3 roots. Now the number of roots is not always going to match the number of intercepts. For example, up here, in this problem, going back to this one, we have 3 roots, 3 answers. My answers are negative 6, positive 7, and positive 7 again. But how many x-intercepts do we have? Just 2. So this has 3 roots, but only 2 x-intercepts. Okay? All right, and then number 2. We got x squared times x plus 3 times x minus 8. So what degree would this be? So if I multiplied all the stuff out, what would my first term be? Well, x squared times x gives me x to the third, times x would give me 1x to the fourth. Okay, so then it's a 4th degree polynomial. What would the end behavior be? Okay, so my exponent is even, so we want to think like a parabola with a positive coefficient would be opening up, which means our end behavior is high to high. And then how many x-intercepts do we have with multiplicity? So let's see, we have 3 factors, so we're going to have 3 x-intercepts. Okay, and what are my x-intercepts going to be? Well, when do each of my factors equal 0? Let's go right to left. This is going to be 0 when x is 8. So 8, 0 is 1 x-intercept. This is going to be 0 when x is negative 3. So negative 3, 0. And then when is this factor going to be 0? Well, it's not a trick question. It's just when x is 0. So we have the point 0, 0 on this graph. Okay, so whenever you have a monomial, whenever it's just x raised to some power, it might be x to the first, x to the second, x to the fifth, whatever, you're going to have the point 0, 0 on your graph. Okay, and then what's the multiplicity of each of these things? Well, I get this answer twice because this is raised to the second power. So 0, 0 has a multiplicity of 2. This has a multiplicity of 1 and 1. All right, next, what's our y-intercept? Well, since we got the point 0, 0, then our y-intercept is also 0, 0. We're only ever going to have one y-intercept. In other words, if I stick in x is 0, 0 squared is 0 times this stuff is still 0. So my y-intercept is 0, 0. How many distinct x-intercepts do we have? Well, 1, 2, 3 of them. And then how many roots are there? How many answers are there? Well, since it's a fourth degree equation, we're going to have 4 answers. So my answers are 0, 0, -3, and +8. Okay, so again here, the roots don't always have to match the x-intercepts. And that's the first page.